Regression by hand. So here we're going to cover how to do an ordinary least squares linear regression by hand. And this is important because it'll show you how the arithmetic operates underneath the statistics. And this will demystify the statistical process for you. It will no longer seem like a magical series of algorithms inside a computer, but it'll be the math that you can see directly in front of you, and you'll see that it's a lot simpler than you think. Now, this is as good a time as any to advise you. Now is this time to start collecting the data sets for your paper. You're expected to write a statistical paper with a multivariate model. In other words, 3 independent variables at least that are predicting the outcome of your dependent variable. It can be on any topic of your choice, not only my specialty. So if there was a paper that you wrote as an undergrad that you really enjoyed, let's try to turn that paper into a statistical equivalent. But to start, you need to get some data. And you'll hear this repeated over and over again. Get more data. The more data you get, the stronger the relationships you have, the clearer the relationships you have, the greater the significance of the tests in the statistical study. So start now looking for data. I have posted a number of data sets that pertain to international relations. I can help you with data sets from other fields. There's a lot of data sets that deal with values, that deal with voting patterns. But ultimately, we're looking for as much data as possible. So get started now. You always have less time than you think. All right, so as a general introduction for the steps for the hand regression, the purpose of doing a regression by hand is to understand the underlying logic. There are proofs that go along with these mathematical procedures. For the rest of the course, we're not going to be looking at this underlying logic. So this is the one time where you get to see how it works. A couple of definitions that you're going to see repeatedly as well as the presentation. Xi refers to independent variable values, where I equals all of the observations or the units of analysis. In other words, if you've interviewed 10 people, or you're examining 10 countries, or you're looking at 10 different time periods, I would be 1 to 10. It would be including all of those individual observations. Yi is the dependent variable. It's what we're trying to explain. And in the hand regression, we're only going to have one independent variable as it affects the dependent variable. X and Y with a bar on top, which we will call X bar or Y bar, means the average or the mean. It's a typical notation for the average. N is the total number of cases or data points, and they total I, where I is equal to 1 to 10, which is like a label for each of the different data points. And epsilon is a very common sign for summation. It tells us to add everything up. You're not going to see it in my presentation, but frequently you will see summation in the notes, and it indicates simply add up those objects that follow. It's also used in more complex calculations, but we're using it as a simple summation sign. So we are going to calculate by hand an ordinary least squares linear regression. Why are we going to do this? Unfortunately, statistics is often used, particularly in the social sciences, as a form of intimidation. People publish using statistics, knowing that other people are not going to be able to challenge them on the substantive issues that they're discussing. It's very important that you recognize the underlying arithmetic, and you see how simple it is, so that when you read a scientific paper that uses statistics and you don't understand it, it's not your fault, it's the fault of the author for not clearly explaining what they're doing. So this is a form of inoculation against that intimidation element that is frequently used by those that use a lot of statistics. Not everyone does that. A lot of scholars just get lost in the complexity of the math, but there is a lot of intimidation, and so let's try to take some of that away. Also, I want you to recognize that the computer that uses statistics is not an adversary. It's not a machine that's trying to hide the math from you, because we're going to do the math here by hand in its full tedious length, and you're going to realize that a computer is an instrument that's there to help you do the math faster and more efficiently. So let's take a look at some of the components I have here. It may not be that easy to read because I've color-coded it, but I've put in white chalk at the bottom with a greater contrast. You can see some of the formula. Here we have N, which indicates the number of cases or observations. And it depends what your unit of analysis is. It could be an individual, it could be a country. Here we have the independent variables in red. And again, there's 10 of them because N is 10. So it says there's 10 observations. And we have the dependent variable in orange, and you can see the 10 observations here. And so each of these columns are labeled 1 to 9. You can see that this independent variable has a value of x. X is always an independent variable. And here you can see this column has y. Y is always the dependent variable. And we have I, because I is sort of an identifier. It doesn't tell us which specific case, but it tells us all the cases from 1 to 10. And we have some other values here in these rows. We have sum, which is the total of the values. We have average, which is the mean. It's the total divided by the number of observations. We have here theta, which represents the standard deviation. We'll get to that later. And here we have S squared, which is the variance, which is very closely related to the standard deviation. And here's some other formula that we'll get into as we do the calculations. But here we've got X bar. It's a variable with a bar across the top, or a line. And that means the average or the mean. And occasionally you'll have a Y hat. And the hat on top of the Y indicates a predicted value. It's a value that we're saying is going to happen, that the math is going to predict. Here we have a Cartesian graph, and you're going to notice that the x values are always here. The independent variables are down here. You can see education in years in this particular case. And here you can see the dependent variable, which is always the y. Now the model of interest that we're trying to solve and we're trying to calculate is how much money do you make based on how many years you've been in school. So here the independent variable is how many years you've been in school, and the dependent variable is thousands of dollars that you're making. Okay, so we have here income in K dollars, or thousands of dollars, and here we have education in years. Education in years, the independent variable, goes from 0 to 20 years, and the dependent variable, thousands of dollars in income, goes from no income up to $100,000. Now you'll see here, this is a bivariate relationship. It means we've got two variables, one independent and one dependent, and it's very easily visually represented with one cause and one effect. But imagine, what if we had a second independent variable, right? Then we would have a cube, and you can see here we have a dependent variable at y, we have an independent variable at x, and we have a second independent variable at z. Now, most models actually have more than two independent variables. So how do we represent it? Well, it becomes visually impossible to represent a model with three independent variables or more. We end up with shapes that are in the fourth dimension. I can show you, however, this is the shadow of a fourth dimensional object projected onto a two-dimensional blackboard. But it's not simply this shape. It's supposed to be rotating, where the inside comes out and then the outside comes in, and it's in constant rotation. In other words, it's too difficult and impossible to represent these graphically, and so we use mathematics, and we use numbers to represent these complex relationships. Right? So here, you can imagine a line going through that which represent the relationship between the independent and dependent variable. When you get to a cube, which has got two independent variables, you're looking at a plane. And when you get to higher levels, you're looking at geometric shapes that cannot be described easily, and certainly not graphically. So most computer software using statistics will not represent the mathematical relationships graphically. You can request it. Most of it will be done mathematically. So if you recall, there are three kinds of statistics. There's descriptive statistics. How much money does the average person make? What's the average time spent in school? What proportion of people have certain kinds of jobs? Depending on your unit of analysis, there's all sorts of descriptive statistics that you could come up with. A second type of statistic is correlational. We want to know the precise relationship between how many years you spend in school and how much money you make. Right? That would be an enormously useful type of information. Right? And it's because of our ability to make correlational statistics that we have polling companies, right? They try to predict which political party is going to win. Or business firms that use statistical marketing analysis to try to anticipate their profits by how many products they can sell. So prediction is a very powerful result of statistics. The third type of statistic is inferential, and we're going to look at that also. And what is the likelihood that the relationship that you're seeing is not real, that it's a coincidence, that it's a false positive? Now, most of the math comes from probability theory for statistics, and most of that came from gamblers in pre-revolutionary France, people playing cards and wanting to know what their chances were of winning. And so they did the math, and the math is accumulated, and in the 19th century, this probabilistic analysis was applied to social scientific data analysis. And we now use this to describe phenomenon, to make predictions, and then to see whether those predictions are real or whether they're coincidental. Okay, so let's get into this. I hope that you have a piece of paper or you have a piece of graph paper. You can follow along and fill in the values. You can see as we go through this long arithmetic process how each of the values are calculated. And you're going to see that it's actually remarkably simple. What's not simple is not the arithmetic, it's the proof. There's a mathematical proof which shows that this linear regression, also called ordinary least squares regression, is the most efficient way of aggregating a scatter plot of data observations into a single line. There is no more efficient way of doing it. Assuming that you satisfied all the requirements and all the assumptions that are required for the data distribution to actually create those results. So as long as you satisfied those assumptions, this is the most efficient way of producing predictions. However, we're not going to be looking at that. That is very, very complicated. What we're going to be looking at are simply the underlying arithmetic mechanics, so that you see that statistics is actually very easy to calculate. It just takes a long time, and that you'll be thankful that the computer does it for you in 1/10 of a second, instead of having to spend an hour with chalk and calculators working out these numbers. So, let's get into the steps. Now, in your notes, I'm going to be referring to serials. Serials are steps. Step 1, step 2, step 3, serial 1, serial 2, serial 3. So don't be confused. When I say serial, I mean S-E-R-I-A-L, which is simply a step in the process of having to do these calculations. And by following on the serials in your notes, you can see step by step precisely what it is that I'm calculating. So the very first thing we want to do is, you recall this from high school, is simply plot those points. Right? We have here independent variables, which indicate the years spent in school. We have the dependent variables, which indicate the amount of income in thousands of dollars. Right? So I'm going to take this, these values, and I'm going to plot it on this Cartesian graph. Okay? I'm going to go through each of these values. So we have individual number 1. They spent 10 years in school. They made $30,000. I'm going to put a nice big data point here. Individual number 2 spent 17 years in school. That's a long time. And they made $60,000. Individual 3 spent 9 years in school, and they earned $20,000. The 4th individual spent 12 years in school and was earning $40,000. The 5th individual spent 14 years in school and earned $50,000. The 6th individual spent 16 years in school and earned $80,000. The 7th individual spent 10 years in school and earned $20,000. The 8th individual spent 13 years in school and earned $60,000. The 9th individual spent 14 years in school and earned $90,000. And the 10th and last individual spent 12 years in school and earned $30,000. So you can see what we have here is a scattering of data points. Right? Now we have a general sense that it goes from the bottom left relatively steeply up to the top right. Right? And so a way of thinking about this, what is the direction of this relationship? As you get more education, it does look roughly like you make more money, right? And rather steeply in sort of this part of the graph. So think of each of these data points as a nail. Imagine I came here and I hammered nails into the blackboard, okay? And then imagine I attached rubber bands to each of those nails. And then I took, in this case, a broom handle, okay? And I put a broom handle here. And I attached those rubber bands to the broom handle. Okay, now those rubber bands are going to be pulling on each other. There's going to be a lot of tension in there. And there's going to be a compromise between the different rubber bands as they all pull this line of best fit, this straight broom handle. And you let go of the broom handle and it shudders and then it stabilizes in an equilibrium. Right? That's what we're looking for. Right? The mathematical proof shows that there's a precise way of calculating this, and that this line of best fit is the most efficient way of fitting this line over those scattered points. Now, there's an important observation here, which is this line of best fit may never actually touch any of these data points. It could pass right through all of them, but give a good sense of an aggregated average best place for this place to go. Now, the actual math is the distance from the nail to the line, and we can let's draw in a line. Let's put in a red line here. The line would look something like this, a line of best fit. And again, you're not going to get a line of best fit in software programs because when you're dealing in multi-dimensional space, you're going to be looking at planes and geometric objects we can't even describe. Now, you're going to notice that the line passes over some points, but for other points, there's a distance. There's a distance between the point and the line of best fit. Right? And we call those distances residuals. They're basically errors. They're distances between the line of best fit and the various data points. And so you can see where the lines are longer, you're going to have much greater tension in the rubber band and a lot greater pressure. Now, the way that we calculate this is we want to minimize the sum of least squares. Okay, it's sort of peculiar, but you would take the distance of the rubber bands, square it, and the math we're going to use has an algorithm where it adds up all those values and looks for a solution that calculates the shortest possible distance on average for each of the data points. Right? And you can imagine in a 3 or 4 dimensional space, it does this on a multi-dimensional scale. The technique we're using here, it's relatively simple for a bivariate calculation. You can do it arithmetically. I'm going to show you later on how to do it for multi-dimensional shapes. It gets a lot more complicated. Not significantly more complicated. But so let's stick here with the bivariate model. So we've done serial 1. Serial 1 was to plot the data points, right? And we did. And we have a rough idea of a line that would fit through there as the line of best fit, right? Also called the regression line. And we're going to talk a lot more about this line later on. We're going to come up with specific calculations and formula for this line. All right, so that's the first task here. So let's now just go through the tedious process of doing all the mathematical calculations. So serial 2, if you recall, is step 2. So step 2, we have to sum up all of xi, sum up all of the independent variables. I'm going to use a white chalk to make it more visible. So that'd be a 10 plus 17 plus 9 plus 12 plus 14 plus 16 plus 10 plus 13 plus 14 plus 12. And of course I've pre-calculated this. So that comes out to 127 if we add all those values up. That is serial 2, step 2. Serial 3, we add up all of yi, all of the dependent variables, 30 plus 60 plus 20 plus 40 plus 50 plus 80 plus 20 plus 60 plus 90 plus 30. And of course I've pre-calculated it, and it comes out to 480. All right, so far so good. Right? We simply summed up these values. In serial 4, we calculate the average of x. Right? And that's going to give us the average, or the mean, or x bar, which is the x with a line across the top. And the way we do that is we take the sum and we divide it by the number of observations, which is 10 in this case. Very convenient. So we know that the average is going to be 12.7. Okay, we write that in here. Maybe it's roughly visible. Now we do the same calculation in step 5, serial 5. We calculate the average of the dependent variable, income in thousands of dollars. So that's 480, which is the sum divided by the number of observations, which is 10, which is going to give us 48. So far, so good. Now we have to do some slightly more complicated calculations. For step 6, for each I, meaning for each individual value of x in this particular case, we have to take the value and subtract from it the average. So the first value would be 10 minus 12.7. So 10 minus 12.7, you can do that in your head, would be minus 2.7. Okay? So it's the value of xi, and the first value is 1, minus the average will give you this value. Now you'll see that I've actually labeled the columns from 1 to 9 for convenience. So right now we're on column 3. Now, of course, I've pre-calculated all the other values. So here you would have 17 minus 12.7, which is going to give us a predictable value of 4.3. And then we're going to have 9 minus 12.7, which is going to give us minus 3.7. And then minus 0.7 for the for serial 4, not serial 4, rather for observation 4, and then 1.3, 3.3, minus 2.7, 0.3, 1.3, and minus 0.7. Right? So we've calculated all of these. We've subtracted from the original independent variable its average or its mean, and we've written the results down here. Now for step number 7, which applies to column number 4 over here, we simply square those values. Now you might recall from high school, a negative times a negative is a positive number. So minus 2.7 squared, it's going to be 2.7 times 2.7 is equal to 7.29. And 4.3, because of course I've pre-calculated this, is going to be 4.3 times 4.3 is 18.49. Minus 3.7 times minus 3.7 will be 13.69. Minus 0.7 times minus 0.7 will be 0.49. 1.3 times 1.3 will be 1.69. 3.3 will be 10.89. Minus 2.7 times minus 2.7 will be 7.29. 0.3 times 0.3 will of course be 0.09. 1.3 times 1.3 will be 1.69, and minus 0.7 times minus 0.7 will be 0.49. Okay, so there we've calculated the squared values in column 4 of the calculations we did in column 3, and we carry on. We're going to do the same calculations now for the dependent variable, which I've color-coded here in orange, and you're going to have yi minus y bar. So the value of y minus the average that we calculated down here. So the first value will be 30 minus 48, and that's going to give us a minus 18. Right? Fairly easy calculation, and we would continue with those calculations. So we have 60 minus 48 is going to give us 12. 20 minus 48 is going to give us minus 28. And then so on, minus 8, and then a 2, and then a 32, and a minus 28. You see, there's a lot of work here. And a computer accelerates this work, but the work essentially is easy. It's literally child's play. You could have young children doing these calculations for you. You don't need statistics to be done by adults. It's a child's game. So now in column 6, we have to continue the calculations as a part of serial 9. We're going to square these values, right? So we have minus 18 squared. 18 times 18 is going to give us 324. Of course, 12 times 12, you guys remember your times tables, is 144. Minus 28 times minus 28 is 784. Minus 8 times minus 8 is 64. 2 times 2 is 4. 32 squared is 1024. Minus 28, we already calculated that, is 784. 12 is 144. 42 squared is a big number, 1764. And of course we have minus 18, which we already calculated as 324. So, a lot of numbers, fairly simple procedure. So that concludes serial number 9. So now we're on to serial number 10. which is cross multiplication. So here we're multiplying columns 3 and columns 5. This is the dependent variable, if you recall, where we did the value minus the average value for the independent variable and for the dependent variable, y minus y bar and x minus x bar. So we multiply those two values together. Minus 2.7 times minus 18. And of course, if you have a calculator with you, right, you can sort of quickly calculate it. Of course, I've pre-calculated these. So this is going to give us a 48.6. And we write this in on column 7. You can see I've done that up there on the top. So let's go put in these cross values. Next one's going to be 51.6. Right? It's going to be 4.3 times 12. Next we've got minus 3.7 times minus 28, which is going to give us 103.6 and 5.6, 2.6, 105.6, 75.6, 3.6, 54.6, 12.6. So this is the calculation of the cross multiplication of columns 3 and 5. And so that was serial 10. That was accomplished quite easily. And so now we're on to doing two summations. In serial 11, we want to add up the bottom of column 7. So we want to sum up these values here. And that would be 48.6 plus 51.6 plus 103.6, all the way down to adding I10, observation 10, which is 12.6. And if we add all those values up at the bottom of column 7, that's going to give us a value of 464. So we put the values in here as a summation, 464. And then for serial 12, we want to square the values. No, wait, I put that in the wrong location. We're going to put this at the bottom of column 7. No, that's in the right location. So we're going to do the sum for column 4 here, which is going to be summing up the squared values of x minus x bar. And so it'll be 7.29 plus 18.49 plus 13.6 and all the way down until we get to 62.1. Until we get to 0.49. And that's going to add up to 62.1. Okay, so we need to come up with these two values. So we've done a lot of calculations to produce these two discrete values, which are going to be very important in the subsequent calculations that we're going to make. So let's take a look now back here. So here we have a line of best fit, a regression line, right? We can see that it's sloped. And because it's sloped, it tells us that for a certain number of values of x, we're going to get a certain number of values for y. We call this a monotonic relationship. As the value of x goes up, so does the value of y. But this relationship could be just as well inverse. You could have a direction like this, where increasing values of x will reduce values of y. It depends on the character of the relationship between the independent and the dependent variable. But what's important here is that we recognize that there's a slope here, and it's a slope that gives us the value from the x to the y. And you can imagine that if you had a straight line going up, it would be undefined, because then the value of x could create any value of y, and so it'd be indeterminate, right? So this slope is very, very crucial. So for determining and making predictions. So you might recall from high school the linear equation, right? Y is equal to mx plus b. Now the precise form and the precise way that the values were represented might have varied depending on what school or what region you studied in, but essentially the structure is the same. You have y, which is the dependent variable. It's the thing you're trying to explain. It's the problem you're trying to predict, is equal to the slope, which is m, which is an angled relationship of the line of regression, times the independent variable plus b. B is the y-intercept. It's where this line of regression will cross over the y-axis. And if we look at this red line, it's going to descend quite a fair bit into the negative range of the y-axis, and it's going to cross somewhere down here. So the y-intercept is a way of adjusting where the line is going to cross over, and then the slope tells us what angle it's at. But essentially, this is a function. We insert the independent variable. We have a calculation here in the formula, and the equation then gives us the dependent variable. Right? That's why functions are so important, because they allow us to make predictions, and statistics uses a function to make predictions based upon the distribution of these cases that we see in the scatter plot. Now, the formula we're going to use here is again, it's sort of tedious, but it's the same linear equation, in this case a bivariate one, a very simple one with one independent variable and a dependent variable. But they require a switching around of the values. So this is the convention in the social sciences. Y hat, meaning the predicted value of the dependent variable y, is equal to bx. Here b is the slope, it's not the y-intercept. X is still the independent variable, plus a, where a is the y-intercept. So it's the same formula, just learn this one for this particular class. So what we want to do now is characterize this line of regression. We want to be able to use it to make predictions, and that's what we're going to do now, using the values that we've come up with and developed here. Okay, so let's go through the calculations for that. It's not long. It's actually quite short because we've already done most of the work. Okay, so for serial 13, we want to calculate the slope. Okay, and the slope could be thought of as sort of the rise over the run, right? Sort of this shape here, right? How many values do you go up, and then how many values do you go, and that's sort of going up in a positive way, and then going to the right in a positive way. Rise over run is going to give you your slope. So that's what we want to calculate here. And the way that we calculate the slope, we want to find out what the value of b is. B is actually formally called b subscript yx. And this is what you're going to see in your notes, but here I'm just calling it b. And b is serial 11 divided by serial 12. And serial 11, if you go back to serial 11, you're going to notice it's the calculation we made, 464, which we insert here, divided by 62.1. Those are the last two values that we calculated. So we're going to have 464 divided by 62.1, and that's going to give us a value of 7.47. That's the slope. So what does that tell us? That tells us that we go up by 7.47 points, and then we go across 1 point. Right? That's essentially the value of the slope. It's 7.47 over 1, although we sort of represent it in a reverse fashion when we show the slope on a Cartesian graph. So we have this value, 7.47. Well, we can't do anything with it yet. So let's do the next calculation, which is the y-intercept. It's the a. It's where the line of regression crosses over the y line in the Cartesian graph. So the formula here is a little bit more involved. It's serial 14. It's going to be a, which is the y-intercept, is equal to y bar minus b subscript yx, which is this value here, which we've already determined, times serial 4, which is x bar, or the average value of x. So that's going to be 48, which is serial 5, which is what we calculated earlier on, minus, and here you've got square brackets to keep both values together, serial 13, which is going to be minus 7.47. So there should actually be a bracket here that captures both of these values, times 12.7, which is the number that we calculated in serial 4. So it's three separate values that come from earlier serials. It's all in your notes, and the notes tell you what serial to go to gather these numbers. And if you're to calculate this out, you're going to end up with a value of minus 46.86. All right, so what do we do with these numbers? Well, we now have enough numbers here to put them into a function. So this is the slope, right? It's the slope. This here is the y-intercept. It tells us where the line of regression is going to cross over on the y-intercept. And we can put them together, and here, this linear equation. So here we have y hat, which is the predicted value. It's what we're trying to predict. is equal to 7.47 times x, which is the independent variable, years spent in school, minus 46.86. Minus 46.86 means minus $46,000, 860. Right? So let's make a prediction. Okay? Let's do a very simple one first. Let's imagine you're in school for 10 years. All right? So 10 years is x, right? That's the independent variable. So 7.47 times 10 is going to be 74.7 minus 46.86 is equal to y hat. Y hat is how much money we're going to make. So we just take a calculator and work that out. So how much money am I going to make if I'm in school for 10 years? 74.7 minus 46.86. I'm going to make $27,000. Wow, look how accurate that prediction is. It's 27.84 actually. So what this is telling us is we find the x value. In this case, we chose 10 years, which is about here, and we follow that up to this line of this regression line, and the regression line refers us over to the y-axis and tells us precisely how much money we're going to make. Right? Let's do this for 20 years. What if I'm in school for 20 years? Let's calculate that. 20 times 7.47 is equal to 149 minus 46.86 is equal to 102. So if I'm in school for 10 years, I'm going to make $102,000. Wow, that's so precise. The incredible thing about this ability to make a prediction is that we can do it with as many independent variables as we want to include. In this bivariate model, we have x. But we could add a z for the type of education. We could add a variable k for the location of the school. It's just so many variables we can add. And each variable that we add adds increasing accuracy to the prediction. You can see how powerful statistics is by being able to make these kinds of predictions. Right? So just to sort of recap what we're doing here, this line is fitted here because this calculation that we did has a proof that shows that by minimizing the sum of the individual errors, right? Remember, the distance from the nail to the stick is an error. It's a residual. Right? It's the leftover stuff that we cannot explain because tragically our math is primitive and we can only make a prediction with a straight line. We cannot have a line wiggling through the different dots. This line is a compromise that goes between the different data points. And it's the most efficient way. This math is the most efficient way of fitting this line to those dots. We cannot make a more accurate assessment using these observations except through ordinary least squares regression, which is what we did here. Okay, so the total of the error, all these errors added up, all these little residuals added up together is what we would term the total error. So this is sort of a discrete display of the power of statistics in making predictions. So let's carry on now to the next step, which is looking at a correlational statistic. So a correlational statistic will allow us to see what is the relationship between the independent and dependent variable captured together in a universal term which we call r squared in ordinary least squares regression. And you're going to see a lot of r squared. Right, here we're going to calculate sort of a small r squared, which is the bivariate correlation between the independent and dependent variable. Ultimately, we're looking for something called the proportion of variance explained. How much of the variation in the dependent variable is explained by the independent variable? X will not predict all of y. X will predict a lot of y, but not most of it, probably, and certainly not all of it, right? So if you were to add more variables, you would get your correlational statistic to improve, and so that's what we're going to look at right now. Okay, so I'm going to remove some of these, create some space down here because we're going to need our linear equation. Okay, so in serial 16, we have to sum the total values for yi minus y bar, which is the bottom of column 6. So we want to total up this value here. 324, 144, 784, 64, 4, 102.4, 784, 4, no, sorry, 1024, 784, 144, 1764, and 324. And when we add up all of those numbers, we're going to end up with 5,360 as the total value. 5,360. Right? So we now go to serial 17. Now in serial 17, we're looking for a value which is b subscript xy. This is the opposite of what we looked at before, which is b subscript yx. Here it's b xy. And here we go to serial 1, serial 11 rather, and we divide serial 11 by serial 16. And serial 11, if you recall, is the calculation we did, was 464. So this is going to be 464 divided by serial 16. And serial 16 is the calculation we just made, 5360. Right? So if we take a calculator and we work this out, this is going to give us 464 divided by 5360. It's going to give us 0.0865. Okay, so that is step number 17. Now step 18, here we're getting to the correlational statistic, which is r squared, is going to be b subscript yx times b subscript xy. In this case, we have a small r squared because we're looking at a bivariate correlation here. This is going to be serial 17, which is what we calculated right here, times serial 13. Now, serial 13, if you recall, is 7.47. It was the slope that we calculated here for the linear regression. And that's 7.47 times 0.0865 is going to give us 0.646. What on earth is this number? Well, this number, you're going to see a lot of it. All right, so a correlation is like a probability. It goes from 0 to 1. 1 means you're explaining 100% of the variation. 0 means you're explaining none of the variation. Obviously, the more variation you explain, the better, right? So what we've calculated here is that 0.646, or about 64%, of the variation in values of y, the dependent variable, which is how much money you make, is explained by your years in education, right? It means, conversely, that about 35.4% of the variation is explained by other things. So this is actually very important. It shows that education explains more than half of the variation in the dependent variable. When you're designing a model, you want to maximize your r squared. Okay, but not to the point of ridiculousness. In the hard sciences, you get correlations of 0.9, 0.95, 0.8. In the social sciences, it's very complex. There's a lot of activity going on. If you get a 0.64, that's a fantastic value. This is a very strong value. If you have a result of 0.5 or 0.4, that's a strong value. Even a 0.3 is a very strong value. If you just think of the sheer number of independent variables that play a role, domestic politics, local politics, personal psychology, family life, how these influence when a country chooses to do something. You can imagine in political science, there's so many other variables that getting a value this high, it almost looks like you're cooking the numbers in order to manufacture a very high valued r squared. So r squared is one of many measures of association, and there are different kinds of measures of association. R squared is one that's most common because about 75% of all the statistics that are used is this, ordinary least squares linear regression, which relies on the r squared. Okay, now you can also calculate the inverse formula, which you can do between serials 19 and 23, but I'm not going to do here because it's simply the reverse of this. It's simply going to show you the variance that's not explained, meaning there's other variables that we're missing that we need to put into the model that's going to give us the balance of the variance explained that we're actually not explaining. Okay? So I'm going to take a quick break here. We're going to come back and look at inferential statistics. What we want to do is capture the ability of the regression equation that we calculated before to make predictions. So in column 8 we have y hat I. Now if you recall with the regression line, it didn't go over most of the points. It was a compromise between the points. So what we want to show is that we can make predictions along that line of regression, because every prediction that occurs will occur along that line of regression. So we take our original formula, which is y hat equals 7.47 times x, that's the slope, minus 46.86. And we're going to insert each of the original independent variables, and that's going to give us a predicted value for y. Now that predicted value is almost never going to be the same as the actual y value. But the ordinary least squares algorithm makes sure that this is as close as you could possibly get using any technique. So this technique will bring the predicted value of y as close as possible to the actual value of y. But they're almost never going to be the same because we're using an algorithm that depends on a straight stick to make a prediction. Okay, so let's drop in each of the values. All right, we could start off with 10. So y hat is equal to 7.47 times 10 minus 46.86. And of course, I've already calculated all of these, but that first value is 27.84. So if you're in school for 10 years and you're this particular individual, this individual should be making $27,000 a year. In fact, they're making 30. So the reality is they're making slightly more money than predicted by the model. Maybe they had an opportunity for a better job that the model didn't predict. There's a whole variety of reasons. For the next individual, the prediction is 80. In fact, they made 60. They did much worse, probably because they spent a lot of time dilly-dallying while they were in university. The next individual is 20, which is right on. There, the prediction is perfect. Right, they were predicted to make 20, and they actually made 20. The next is 42. In fact, they made 40, so they did slightly worse than they should have. The next individual is 57. They did much worse. They only made 50, not 57. The next individual is 72. They actually did 80, so they did better than predicted. The next value is 27, which is higher than the value of 20. Then a value of 50, which is lower than 60. A value of 57, which is much lower than 90. This individual really did their education outside of school. And the last individual got a 42. So you can see that we can go back and then make predictions and then compare how strong the predictions are with the actual outcome values. So as I said earlier, we're not actually going to calculate column number 9 quite yet, because it's sort of a trivial arithmetic exercise where instead of looking at the proportion of the variance explained, the r squared, if you recall earlier, which is the one measure of how much of the change in the dependent variable is predicted by change in the independent variable. This calculation here is simply the reverse of that, so I'm not really going to spend any time on it. So what I want to talk about now is probability, and the probability of gambling, say with dice. I have here a container with dice. So what I'm going to do is draw your attention here to this normal curve. All right, and what I'm going to do is I'm going to roll dice, and I'm going to add up the dice. And I've got 3 dice here, 6-sided dice, and the values range between 1 and 6. And so you can imagine I could roll 3 1s. And so the lowest value is a 3, and the highest value could be 3 6s or an 18. All right, so let's look at the shape that emerges as I roll the dice, and I then draw a little cube on top of each of these numbers. All right, so there I rolled a 14, little squiggle there. Here I rolled a 9. Here I rolled a 10. This will take a few minutes, unfortunately, because we've got to generate a whole bunch of numbers. There I rolled an 8. Here I've got a 12. Here I've got an 11. Isn't that peculiar? I'm not getting a lot of 18s or 3s. Here I've got a 13. This is, wow, it's like a hidden thing in the machine. Here's 12. Here is 8. Here is a 10. Ooh, a lot of clustering in the middle. Right? Here's a 7. All right, we're moving a little bit to the edges there. Here's a 9. Ooh, you can see a sort of a build-up going on in the center there. Oh, another 7. That's rather unusual. Here is another 7. That's fairly unusual. Here is an 11. Here is a 12. And here is another 12. And here, oh, this is very rare. Here's a 16. Wow, all there on its own. And here's a 9. And here's another 12. And here's another 7. And here's another 13. I think you see where this is going, right? Oh, this is unusual, 15. And I'm going to finish here with a 9. So we have, not a lot of values here at the tails and sort of a lump in the middle. This is a natural occurrence in nature, as predicted by the central limit theorem, that stochastically any behavior that has a distribution, or any phenomenon with a distribution, if it's replicated, will create a normal curve. This is such an important observation in nature that in a court system, you no longer have to argue that normal curves exist in nature. You can simply assume it before the judge and then use it in your, say, anti-discrimination case. So this is a natural occurrence. It's universal. And depending on the structure of the data, it can take different shapes. This here is a normal curve. Now the curve we're going to look at here is a t-statistic. We're also going to look at the f-statistic. But the t-statistic started out as a university project by a student of the manufacturing of beer in Ireland, Guinness specifically. And he went to study at university to figure out how to improve the quality of beer. And this student needed a curve in order to do hypothesis tests. And so he created a normal curve by counting the length of the middle finger of prisoners in England. And he discovered that it was a normal curve. We use the normal curve and the logic behind it, which is captured by the central limit theorem, to test whether, when we see a phenomenon and a distribution of behavior, whether that is a real behavior that characterizes the population, meaning all behaviors of that type in the universe, or whether we're looking at a coincidence or a false positive. This is very important because inferential statistics is magical. As you would notice if you were to take a course on surveying, and you might still, if you have a population of 10 million people, or 100 million people, or 1 billion people, if you interview only 1,500 people, almost without regard to the size of the population they come from, you can make predictions to plus or minus 5% as to how they're going to vote. That is virtually magic. You're saving huge amounts of money. You're able to make incredible generalizations from a small sample to enormous populations. And so what we're doing here as social scientists, we're interested in the relationship between going to school and the amount of money you make on graduation, but we're also interested in Can we take this model and export it and apply it to larger populations? Can we generalize the values? And that's why we need the central limit theorem, because the true power of statistics is not making predictions, it's not showing a correlation, it's generalizing from a small sample to enormous populations. That's where the cost savings come in. Okay? So let's take a look at that. Okay, we've seen here that we've created a normal curve. We actually know a lot more about normal curves than just this. We can actually come up with characterizations as to where people lie within that curve. Right? And that's why standard deviations, here represented by the letter theta, are so important. So here we have a normal curve. The red line down the center represents the mean. It's the average value, whatever that distribution is. Right? And of course, different types of things have different distributions. The age of your car, the age of your house, the age of your dog will all have different distributions. Because of course there are no negative ages. Right? So you're going to have sort of a clumping and then sort of a tailing off, right? So there are many, many different distributions for different types of data. But this here is a normal distribution that we use when you do hypothesis testing to see if an observation that we found in statistics is actually generalizable to the population from the sample. So you here see the mean, you can see here the mean, and you can see a theta on either side. Each theta represents one standard deviation, right, which you might recall from earlier classes. The power of a standard deviation is that we can do hypothesis testing with it, and we can characterize how members of a population are distributed within that bell curve. So the rule is 68% of people, if you have a bell curve in which you've got not a discrete number of values, but an infinite number of values, an infinite number of observations, and you get a perfect normal curve, 68% of the individuals will be within one standard deviation of the mean. 95% will be within two standard deviations of the mean. That means plus or minus two standard deviations, right? 99% of people will be within three standard deviations of the mean, right? With only 1% left off in these asymptotic tails. The asymptotic tails means they're parallel to the bottom of the graph, but they never touch. They go off for infinity, right? Because we're looking at an infinite number of units of analysis inside this distribution. Okay? So, let's take a look at some of the things we can do with this, okay? Now, I should first show you some math on applying standard deviations, and then we're going to talk about significance tests, right? Because all this comes back to analyzing whether we can generalize this. We use significance tests to see if we can do that. Okay, so this is serial 24 and 25. If you recall, we didn't do serial 20 to 23 because it's simply the reverse of the amount of variance explained, and it would have filled out columns 9. But you know, frankly, that's sort of a trivial showing off of math skill. It's not actually learning something that you're ever going to use again. So let's look at the standard deviation for the independent variable. So we have here numbers of years in school. We want to make a sort of an assessment of what is the range of years of school around the mean that'll contain 68% of those people, or 95% of those people. All right, so let's do the standard deviation. Now, we start with the variance. The variance is symbolized by the s squared, and it's basically the sum of xi minus x bar squared. Okay, and we divide it by the total number of observations. So that's serial 24. So how do we do that? Well, we've already calculated it. It's basically serial 12, right? Which is the bottom of column 4, which is 62.1. We've already calculated that quite a while ago. So 62.1 divided by the total number of observations, which is 10, will give us 6.2. Right? This is going to give us our theta, 6.21. Sorry, our 6.21 is going to be our variance. Now, to get the standard deviation, we take the square of the variance, right? The variance is s squared. And so the square of 6.21 is going to be 2.49. So how do we use this? Well, what is the average time spent in school? Right? We already calculated that. It's 12.7. So we know that the average time spent in school is 12.7 years, plus or minus one standard deviation, right? So it's going to be 12.7 plus or minus 2.49 years, our standard deviation. And we could calculate that with a calculator to get more precise. 12.7 minus 2.49 is going to be 10.2. 12.7 plus 2.49 is equal to 15.1. So 68% of people on this list and in the general population will be in school between 10.2 and 15.1 years. And we can extend this to 2 standard deviations. All we have to do is multiply 2.49 by 2. 2.49 times 2 is equal to 4.98. So we could recalculate that. 12.7 plus or minus 4.98. So what would that look like? Well, it would be 12.7 plus 4.98 plus 4.98. My chalky fingers are jamming up the buttons. That's 17.6 at the upper range. The lower range would be 12.7 minus 4.98. That's 7.72. So 95% of people will be in school between 7 and 17 years. Right? So it's a useful way of characterizing data, because we can then group and see how common it is for certain characteristics to fit within certain ranges of values. Now we can do the same to the dependent variable, right? How much income? Now we know the average income, we've already calculated it, it comes up to $48,000. So the average income is $48,000. What is the value within one standard deviation? Okay, so let's go and calculate that. So this is serial 25. Again, it's exactly the same formula. It's the variance, or S squared, is the sum of yi minus y bar, which is the y minus y average, squared, divided by the number of observations. We already calculated this in serial 16, which is the bottom of column 6, which was 5,360 squared, divided by 10. So that's going to give us a square root of 536 for the variance, which is going to give us a standard deviation of 23.15. So 23.15 down here, right? And the value for, that's the standard deviation, 23.15. Put that up here, 23.15. Right? So we can see right away with one standard deviation to be plus or minus 23.15. So that's going to be the square root of 536. Basically 5,000 divided by 10, which is the number of observations. So we have plus or minus 23.15. All right, so we can calculate that very, very easily. One standard deviation, 68% of people will be making between 48 minus 23, I should be able to do this in my head. 68% of people will be making $25,000 to $71,000, and 95% of people, we can just sort of subtract from this, 2 plus 94, 95% of people will be making between $2,000, which is a pitiful amount, to $94,000. So we can use standard deviations to make characterizations of ranges of values within which people fit. Okay? But frankly, that's not a very important application of standard deviations. The importance of the application comes now. So what I want to do now is calculate 2 inferential statistics. The first one is called the t-statistic. You will see this when you run your regression using a computer. The t-statistic tells us for the individual variables, what's the likelihood of the relationship being real? Real enough that we can extrapolate it to the population from the sample. Because very often you'll see a relationship. You could have a small store, and everyone that comes into your store to buy a cake also wears a hat. And you think, you're imagining there's a relationship between hat wearing and cake eating. But there may not, in fact, be a relationship at all. It might just be a coincidence. It might be that you've been in that store for many, many years, and on this one day, there are people who happen to show up with hats who like cakes. That's quite possible. But if you're going to spend public money on policy, you want to make sure that you're not generalizing from false assumptions, right? So we use the distributions of the population, the data distribution, to try to make extrapolations as to whether the relationship we're seeing is real, right? Is there a hat convention in town next to your bakery that's causing people with hats to buy your cake? Okay, so that's the t-statistic. T-statistics are valid for individual independent variables. We only have one independent variable here, which is the amount of years spent in school. But if you had a model with multiple independent variables, each of those independent variables will get their own t-score. And some of the variables will be significant, which means they can be extrapolated, which means there's a real relationship there. And others won't have a relationship, and you probably want to take them out of your model. The second statistic we're going to look at is the F statistic, and that is a statistic for the entire model, including all the independent variables at the same time. And it's basically asking the question, can we generalize from the entire model? And so both of these statistics are useful. These significance tests, as we call them, tell us whether we can generalize from the data to the larger population. And ultimately, predictions are very useful. But as social scientists, we're trying to create models for large collections of phenomena. And so significance tests are absolutely important. And if you don't have significance in a relationship, then it means not only can you not generalize to other cases in the population, but probably you can't generalize to the same number of cases you have in a previous time period or in a later time period. It's just a temporary coincidence. Okay, so let's go calculate the t-statistic. And there's a lot of serials here, there's a lot of math, it's very tedious, you just have to go through all the steps. There's really no escaping having to do these various steps. So, column 10, serial 26, we have to calculate we have to multiply each x times each y. So it's an xi times a yi. It's basically column 1 times column 2. And then ultimately, we're going to take the sum of those values. Right? So you would multiply 10 times 30, which is going to give you 300. Really not very exciting. 17 times 60 is going to give us 1020. And then 180, I've already, of course, calculated this. 480, 700, 1280, 200, 780, 1260, and 360. And so we then sum up the values, and the value at the bottom is going to give us 6560 for the sum. 6560, and that's serial 26. For serial 27, we product the sum of xi times the sum of yi. So here we're looking at serial 2 times serial 3, and so we would be looking at 127 times the value of 480, right? Which is this value here times the value of 480, and that's going to give us a free-floating value, which doesn't go on the chart, at 60,960. So in step 28, we want to take the sample estimate numerator. So here we're going to have labels for the different portions, and it's going to be serial 26 minus 1 divided by the number of cases times serial 27. So it's going to be 6560 that we calculated earlier in serial 26 minus square bracket 1 over 10 times the value up here, which we will insert. And this value is going to give us a value of 464. And this value of 464 is going to fit into the model later on. Serial 29 is the sample estimate denominator, part 1. So here we're going to take the sum of xi squared, which is basically column 11. So we're going to sum up xi. So you take xi and then you will square it. So you take this value, you square it, and then you add up all the values as they descend to the bottom. So it'll be a 2, 8, 9, 8, 1, 144, 196, 256, 100, 169, 196, 144, and when you've summed it all up, serial 29, bottom of column 11, you end up with 1,675. So that's the end of sample estimate denominator part 1. For the sample estimate denominator part 2, it's 1 divided by the number of cases. Again, we have an I of 10 times the sum of xi squared. So it'll be 110 times 127 squared. And this is going to give us, if we calculate this out, 1612.9. So that was step 30, serial 30. So step 31, sample estimate denominator, the final calculation. Here we take serial 29, which we just previously calculated. We subtract from it serial 30. So it's going to be 1675 minus 1612.9, which is going to give us 62.1. So still there? Step 32, we want to sample, so step 32 is we want to do the sample estimate, the final calculation, which is going to be serial 28 divided by serial 31 that we just calculated, which is going to be 464 divided by 62.1, and that's going to give us 7.47. You recognize that? Yeah, it's the slope. Exactly. Okay. So this is a sort of a recalculation of sorts, but applied to a significance test. So serial 33 is the standard error. All right. Here we want to calculate first the numerator and then later the denominator. So the numerator is a sort of fairly complicated calculation. It's yi minus y hat. So this we've already done. We did this in serial 21. For a previous part. So that's going to give us a serial 21 divided by n minus 2. So we're going to have n because we have, that's the number of cases, and we're going to subtract 2 because it's a convention, 1 for the independent and 1 for the dependent variable. And it's a way of increasing the confidence of your values and to be more conservative by assuming you have less cases than you actually have. Because generally, if you want to improve significance, get more cases. And you'll hear that mantra over and over again from statistics teachers. You want better results, you want stronger results, you want better significance, you want a better measure of association, you want to make better predictions, get more cases. Right? Getting cases is difficult. It means sitting in a lobby, distributing surveys for 10 more hours. It means calling more people. It means going to the library and getting more data. So getting data solves problems. It makes your significance better. And it explains why we take such conservative values. We pretend to use less cases when we do the calculations than we actually have. So we have 1893 as the value from serial 21, which goes back a ways. So it's 1893 divided by 2 cases less than we actually have. So it's divided by 8. And that's going to give us 236. Okay? That's the standard error numerator. Now we want to calculate the standard error denominator. Here we're going to take the root of the sum of xi minus x bar squared. Okay, which is actually, again, we've already done this. This is the root of serial 12. And the root of serial 12 is right here. It's 62.1. So we're going to take the root of 62.1, and that's going to give us 7.88. Okay? So there's 7.88. So here is the numerator that we calculated. There's the denominator that we calculated. And so in serial 35, We're now going to calculate the standard error. It's sort of a very long, complicated formula that you can read in your notes. It's the root of the sum of yi minus y hat squared, close bracket, divided by 8 cases, 10 cases minus the 2 variables, independent and dependent, itself divided by the root of the sum of xi minus x bar, which is the average, squared. Okay, and this is going to give us the root of 236 divided by 788. So it's going to give us the root of this, right? And that is going to be the root of 30. And you would plug your calculator, the values into your calculator, and out would come 5.47. Boom. Okay. So now we want to calculate the t-statistic. Okay, so the t-statistic is the sample estimate divided by the standard error. This is the standard error. Okay? So we're going to take the standard error and we're going to divide it into the sample estimate. Sample estimate is serial 32, which is the slope. So it's going to be 7.47 divided by 5.47, and this number is going to be 1.36. Okay, so what are we going to do with this number? This is the critical t-statistic that we just generated. All right, so before we wander off, I need to give you an idea of the structure of how we do significance tests. We always assume there's no relationship. Okay, sometimes this is called the null hypothesis. We assume there's no relationship. And when we do a statistical analysis like this, we assume that there is a relationship. And what we want to do is, in fact, we want to show that there is a relationship. Now, a correlation is not a relationship. You could have a correlation that's not causal, that's entirely coincidental. Right? So you could have a high correlation and no relationship. We want to be able to detect that. A significance test like this will help us detect that. And it does that by using probability. So, the way we need to think about a significance test is a boxing match. It's a boxing match between the null hypothesis, there is no relationship, against the idea that there is a relationship. Now, as you know, there is no proof, right? We cannot prove anything deductively. However, we can falsify. And so the whole logic of a statistics test is that we're going to falsify or attempt to falsify. Maybe we're going to fail. We're going to attempt to falsify the idea that there's no relationship. Right? That's the standard way of doing significance tests, right? You're setting up a fight between two interpretations of the data, and you're using a chart to determine which is going to be the correct answer. So I'm going to sort of read off the formal definition here. Significance tests in statistics give an estimate of the confidence an observer can have of the results. Specifically, the probability that the relationship observed are the result of random probability or are a real association. Now, there are different standards. If you're in a pharmaceutical company, you're probably looking at a tolerance of 1/10 of 1%. Because 1/10 of 1% of people, if you're doing a drug trial, is going to injure a lot of people if you don't have a high degree of confidence in the reliability of whatever agent or drug that you're manufacturing. But the social sciences is very chaotic. There's so many variables. And I don't mean chaotic random, I mean chaotic meaning complex. There are so many variables at play, we have to be a lot more forgiving. So we are at a very high threshold of 5%. We expect that 5% of the time there's going to be a mistake. So we are willing to accept a significance test that's no worse than, that doesn't have a standard worse than 5%. And that's pretty high. If you're an engineer, you're looking at less than 1%. If you're looking at a significance that's worse than 10% or worse than 5 to 10%, then that's past our threshold, and we deem that event not real. We deem it a coincidence. So significance tests are therefore hypothesis tests. You're trying to falsify the existence of a false positive. And if you fail to falsify the existence of a false positive, then the alternative explanation, the null hypothesis, that there is a relationship is confirmed. So you're trying to show there's no relationship. And then when you fail to show there's no relationship, the result is there is a relationship. And that's how we structure these significance tests. So we are now going to take this value and we're going to apply it to a chart. And I'm going to show you how to interpret that value on the chart. All right, so now when you use your computer, it's going to be done automatically for you. But when you're doing it in a non-computer age, as we're going to do it here, I'm going to show you the chart that is at the back of every statistics manual. And you should be able to interpret and read these charts and not become dependent on the computer all the time for producing these results. So we made our t-statistic calculation and we came up with a value of 1.36, which was a sample estimate divided by the standard error. So all those calculations have produced this t-value. We now have to take this t-value and we take it to the t-statistic table, which you see here before you. Now, if you recall, in the social sciences, we normally go with a level of significance of 5%, which is represented by the 0.05 column that you can see at the very top, right here. So we're interested in the numbers that lay below this value to see whether we have a false positive in the relationship. Now, if you recall, the t-statistic refers to the likelihood of there being a true relationship between the independent variable and the dependent variable. In this case, the independent variable is the year spent in school. So the way we navigate the table is when you look at the left side column, we're looking there at V. V represents the degrees of freedom. Essentially, we're looking at the number of cases, and this is why having more cases is always so important. You're more likely to get significance if you have a large number of cases. And if you look at the very bottom of column 7, you'll see the infinity sign. That, of course, is the ideal case, having an infinite number of observations, which is what you saw in our normal curve. So you take the total number of cases, and in this case we have an I of 10 observations, 10 individuals. You subtract 1 degree of freedom for the coefficient, meaning the one independent variable we have. If we had more than one independent variable, we'd do more than that. And we subtract 1 degree of freedom for the intercept, if you recall. That's the part of the linear equation in which the line of regression passes through the y-axis. So we're going to have an 8. It's going to be 10 minus 1 minus 1 equals 8. And so we look at the intersection between a v of 8 and we find a value of 1.86. So this is the critical t value from the table. And essentially the test is this simple. The value of the t-score that we calculated from our regression should exceed the critical value on the table. But we only calculated a 1.36, which is less than a 1.86. And so this significance test fails. In effect, the null hypothesis is unfalsified. The null hypothesis that there is no relationship. And this means that we can't confidently generalize from our model to the larger population using that one independent variable. It doesn't mean other independent variables are not significant. And when you have a model with multiple independent variables, it's very likely you're going to get different levels of significances for the different independent variables. This is an addendum to the discussion on the generation of the t-statistic. On the blackboard, I wasn't entirely clear. I didn't fall through all of the sequences in detail. And you can see here a part of an Excel file representation of exactly what you saw on the blackboard. And you can see columns 8, 9, 10, 11, 12, 13, and 14, where column 8 was the predicted value of the dependent variable, y hat. And you can see column 9, where it was y minus y hat, which was then squared. And then you can see columns 10 through 14, which were used to generate the t-statistic. Column 10, you've got basically the value of x times y. And so it's a very simple calculation that you did see generated on the board. And then you can see in column 11, xi squared, which is simply the x value squared. We also did that on the board. And then those two numbers then fed into the calculations of the t-statistic. So where there was lack of clarity was in columns 12, 13, and 14. And you can see the formula for all three of those separate columns. For column 12, you can see it's yi minus y bar, y value minus the average of y minus b times xi minus x bar. And you're going to see that generates the values there. And then you're going to see simply the squaring of those values in column 13. So 13 is going to be the values in whatever cell in column 12 squared, and that's going to give you the values in 13. When you sum that up, it's going to give you your value of 1893. And then you've got column 14, which is the predicted value of y minus the average value of y squared. And again, you get those individual values, you sum them up, and then you get your output value of 3,466. So it's a lot easier to show you on an Excel file than a blackboard, but blackboards are archaic and arcane, and it's how people have been doing math for probably thousands of years, where Excel files are only a few generations old. Now, the F statistic has a different distribution than the T statistic. It has this distribution. It starts off at 0 value, and then it extends out with an asymptotic tail, meaning a tail that goes on for infinity, parallel but never touching the x-axis. So the F distribution captures things like age or height. Like, there is no negative height, there's no negative age, and yet there's no upper limit to height or age. But there is a drop-off. You have fewer tall people, and people expire before reaching very, very late ages. So the F statistic is a lot easier to calculate than a T statistic. It's got 3 essential parts. It's got the total sum of squares, the explained sum of squares, and the residual sum of squares. Residual means left over. In other words, this is the unexplained portion. So an F statistic is comparing what we do know about the variance explained in the model versus what we don't know. And it makes an extrapolation off of that to see if there is the likelihood of a false positive, whether or not the relationship is a coincidence. So let's go ahead and calculate it. It's much easier to calculate than a T statistic. So the total sum of squares is calculated as the sum of yi minus y bar squared. Right, that's basically column 6, which we already calculated, is 5,360. So it's from previous calculations that we've already done. The explained sum of squares is the sum of yi hat minus y bar. So yi hat is the predicted value minus the average value. And that would come from column 7. So we would have to actually calculate this out. So you would take the formula. We've already calculated the y hat, which is over here, and we subtract from the y hat the average value of y, which we have down here. So each of these values minus 48, and then we take the sum of those values, and those values are going to be 3466. And so this, I'm not going to calculate that here because it's relatively simple yet onerous, but you'll have the privilege of calculating this. And the next component is the residual sum of squares. It's the part that we have not explained. And it's basically the TSS minus the ESS, or column 6 minus column 14. It's going to be 5360 minus 3466, and that's going to leave us with 1893. All right, so that's RSS. So to get the value of the F statistic, it's going to be the ESS, which is 3466, divided by the total number of cases, which we know to be 10, divided by the RSS, which we've calculated at 1893, divided by the total number of cases, which is 10, minus the number of independent variables, which we know to be 1. There's simply x, which is the year spent in school, minus an additional 1, which is the k, or a constant. So that brings us down to a divisor of 8. So 3,466 divided by 10 divided by 1893 divided by 8, and that's going to give us a result of 14.6. And so we're going to now apply that to the F statistic chart. Now this is the F statistic table. You're going to notice that we've already specified the level of significance as the 5% level, and here we chose the specific table that refers to that. Now for the F statistic, this is a significance test of the totality of the model and whether we can generalize from the sample to the entire population. We calculated an F score of 14.65 when we did our calculations. So now we have to compare that to the critical value on the table. So how do we do that? Well, the first number we look for is V1, which you'll see across the top, the degrees of freedom for the numerator. In this case, it's the number of independent variables, and this is a bivariate relationship model. So we're going to look at the column with one independent variable at its top. We then look on the left-hand side, V2, and that's the degrees of freedom for the denominator, and that typically means the number of cases. And again, if you look at the very bottom of the left-hand column, you'll see the infinity sign, which indicates more is always better for the number of cases. And you're going to hear this mantra many, many times. Get more cases and you solve a whole series of problems in the statistics. In fact, one of the biggest problems in international relations, specifically my field, is we only have 200 countries and we only have recorded data for about 2 centuries and reliable data for a lot less than that. We are starved for information and cases in international relations. If you're a Canadianist and you have millions of voters, you're much better off in terms of establishing significance. So in this particular model, we have 10 cases. So we will choose the 10 on the left-hand side, and we look at the intersection. And the intersection is 4.96. That's the critical F statistic value. For us to falsify the null hypothesis, which is the default hypothesis, that there is no relationship between the totality of the independent variables in the model and the dependent variable, and whether we could generalize this from the sample, here, the 10 cases, to the entire population, which could be infinite. In order to falsify that there is no such relationship, our calculated F statistic must be greater than the critical value. Now the number we calculated was 14.65. The critical value is 4.96. So indeed, our calculation of the F statistic exceeds the critical value, and therefore the null hypothesis of there being no relationship is falsified. And so the remaining hypothesis, which is that there is a relationship, prevails. It prevails because the null hypothesis was falsified. So you have this peculiar outcome where we can't generalize from the independent variable, but we can generalize from the model as a whole. And again, these are two different tests, and you do have this issue of compatibility, which is curious, and very often you'll have a test where several independent variables will be found significant, but the overall model won't be. Or several independent variables will be found to be insignificant, and the overall model will be found to be significant. So it shows you that even though statistics are in the hard world of numbers, you still don't have complete tangible certainty when doing statistics. Statistics, to a certain extent, is appealing to artistic